In this video, what we're going to look at is solving two of the most common examples of shapes using Gauss's law, right? So there's two main symmetric shapes that we'll use in a non-calculus version of this course, which is a flat plate, either an infinite sheet, like a piece of paper that goes on forever, or like a little section like this, right? Just that's a plate, or a sphere, like a charged, either a spherical distribution or a conducting sphere. Okay, so the first one is a flat plate. So let's say we want to know the field from a flat plate at, we'll call this point P, right? So this plate is positively charged, right? And it's got an electric field coming out from it, and it's uniform, right? Because all these field lines are 90 degrees to the surface. And so we want to know what's the electric field at point P, right? That's what we're trying to solve for. And so you would be tempted maybe to say like, oh, well, I'll just get the distance and do KQ over R squared, right? But this distance isn't going to matter, and we'll see why. So first, let's remember, we know Gauss's law is the electric flux is equal to the enclosed charge divided by the permittivity of free space. And then I'm throwing this in there. This is the surface charge density. That's the Greek letter sigma. That's equal to the total charge on the surface of the object divided by the total surface area of the object. Okay, so let's draw a Gaussian surface for this problem. And so you want your surface to encompass the point that you're looking for, but you also want it to be kind of symmetric to your shape. So what I'm going to draw is a cylinder that does this, and it kind of sticks through like that. So imagine like a piece of paper and a toilet paper tube, and you jammed it through like that, right? That's my Gaussian surface, because all these lines are either parallel or perpendicular to it, which makes solving for the flux easy. Okay, so I know this cylinder, we talked about cylinders before, there's three areas, right? There's A, B, and then we'll call this flat part around it C. So A and B are the ends, and C is like a toilet paper roll. It's the part the paper goes around, right? So if you look at it, A and B are going to have flux, right? Because there's field lines passing through them, and they're passing through at 90 degrees. But C, the surface runs parallel to those field lines. So for C, you're not going to have any flux. So that makes it easy, because now I only have to deal with A and B. Okay, so let's use Gauss's law. The electric flux equals the enclosed charge over epsilon naught. So the electric flux is equal to EA, right? So let's get the total flux. So if I look at B, the flux through B is equal to the electric field times the surface area of this little circle, which I'll call little a. And then A is the same thing, right? So I'll say that the electric field at B and the electric field at A are both this E, that electric field, times the surface area of that circle at the end of the cylinder. Okay, so the total flux is two of these, because you have fields pointing out both sides. So for this, I'm going to substitute in 2 times the electric field times the area of that little circle. And there's nothing from C, so that's why there's nothing in that term, right? So the flux from C is 0. Okay, so that equals the enclosed charge over epsilon naught. So now if I solve for E, I end up with that. Okay, so let's simplify. I could stop there, right? But let's make this in terms of the shape, right? Because right now I'm in terms of the enclosed charge, and that doesn't really help us much, right? So see where this thing passes through right there and right there? Let's look at just that part where it's passing through. Okay, because that's the part that this enclosed charge and area talks to. Okay, if surface density, right, surface charge density, is equal to total charge over total surface area, if I take just a little segment of it, that's also got to be equal to that, right? Because it's like if I take a container of water and I take some water out, the density of the water that I took out is the same as the density of the water that was in there, right? I didn't change it by taking it out. So if I look at just a little segment, it's got to have the same surface charge density as the entire shape. So I can set the charge density in here equal to the surface charge density. So the inside here, it's the enclosed charge over little a, right? So in the little circle is this one, and in the whole thing is this. So I can swap in big Q and big A to end up with this And now I know the electric field at point P anywhere is the total charge of the plate divided by 2 times the surface area of the plate times the permittivity of free space. All right? And notice this doesn't say anything about R. So this is all assuming that we're close enough to the center. The edges are far away that we're not getting edge effects, right? So it's all in a uniform field. There's no distance here. That means that no matter where you go in this field, the electric field is going to be equal to the charge of the plate divided by 2 times the area times a constant, right? That's good stuff. That tells you anywhere in here it's going to be the same, and you can calculate it just by knowing the properties of that plate. Something else to notice too is this electric flux for a shape like this is 2 times the electric field times the area, right? Because this charge and area canceled out. All right, so now let's look at another example, which is a sphere inside a shell. I mean, it could be any spherical shape, right? But I'm going to show you this because I can knock 3 things out at once, right? So we're looking at a sphere, a conducting sphere inside of a conducting shell. And so notice over here I threw in what we learned from the last one about planar symmetry. So if you have something that has 2 sides where the electric field's coming out, you can call the electric flux 2EA. And if you had something that was only one side, for instance, a plate where the field only came out one side, it would just be E times A, right? So those are pretty simple. Anytime you have that shape, you can use this. So let's look at a sphere, right? Let's say I want to solve for the electric field at 3 points. So I'll call that point A, and I'll call point B somewhere inside here, and I'll call point C down here. Okay, so I want to solve for the electric field at A, B, and C. And so what I have is a sphere that's charged, Q1, and it's surrounded by a shell, a spherical shaped shell that's charged with Q2. Right, so both of them have charge, and they're both conductors. So let's do A and C, because B is a special case. So for A, right, we always draw a Gaussian surface. So I'm going to draw like that, right? And so to keep symmetry, like to make a Gaussian shape, you want to keep the symmetry of the problem that you have, right? You want to make all your field lines point perpendicular, because then you don't have to go solving anything, right? So here, this is a sphere. I'll just draw another sphere that encloses it, and it's perpendicular to the field lines everywhere. So right, this charge would have field lines pointing out radially. So my Gaussian surface is going to be perpendicular to all those field lines. So let's write Gauss's law. The electric flux is the enclosed charge over epsilon naught. And this is equal to the electric field times the surface area. All right? All right. So let's solve for E. So E is the enclosed charge over the area times epsilon naught. And so remember, the area of a sphere is 4 pi r squared, right? So I'm going to call this little r, and I'm going to call this big R, because I'm doing A and C. And I know that K, Coulomb's constant, is 1 over 4 pi epsilon naught, right? So I'm going to make 2 substitutions here. I'm going to substitute this in for A, and then I'm going to use Coulomb's constant in a second. So this is equal to the enclosed charge over 4 pi r squared epsilon naught. So now, see where this is going to come in? K is 1 over 4 pi epsilon naught. So I have a 4, I have a pi epsilon naught. So I can rewrite E as the enclosed charge, right? So let's substitute in what's the enclosed charge. Q1 is what's inside my Gaussian surface. So Q1 is going to be my enclosed charge, right? And then I'm calling K 1 over 4 pi epsilon naught times K over R squared. And so if you look at that, that's the same equation as the electric field from a point charge. Remember when we solved it, just like when we were starting out with fields, the electric field is KQ over R squared, right? You get the same thing, because no matter how big this thing is, it's still, when you get far enough away, it behaves like a point charge, right? So even though this thing is outside it influencing the field, at point A, the electric field is just due to what's inside. This is why Gauss's law is good stuff. Okay, so let's do C. All right, so C is the same process. So we start with Gauss's law, right? And I'm going to call that E times A equals the enclosed charge over epsilon naught, right? And so that means the electric field is the enclosed charge over 4 pi big R, right? Because now I'm doing to point C, so I forgot to draw my Gaussian surface, right? I just skipped ahead. There's my Gaussian surface, right? I just draw it at C. Times big R is the radius of that circle, right? So 4 pi times big R squared times epsilon naught. And so let's make the same substitution, right? 1 over 4 pi epsilon naught is K. So I'm going to get rid of the 4 pi epsilon naught and call K. And then the enclosed charge is going to be everything inside my big sphere, which is Q1 plus Q2. So electric field is K, right? Got rid of the 4 pi epsilon naught, times Q1 plus Q2 over R squared. Notice it still looks like a point charge, right? This thing is shaped like a sphere. It's behaving like a point charge if I'm outside of it. So if you're trying to get the electric field at some point over here, this whole thing is going to act like it's a point charge of whatever the sum of the charges inside. So this could be negative and this could be positive. They could both be negative. It doesn't matter, because when you get to way out here and use Gauss's law, it just matters what's inside that surface. Okay, so you can see from the example we just did, if you have something with spherical symmetry, we can use this shortcut just like we did for planar symmetry. If we have two sides, you can say the flux is 2EA, or if you have one side that's got field coming out, it's just E times A. So here, 4 pi R squared is the surface area of a sphere, right? So we can use this shortcut when we're solving Gauss's law, okay? So let's look at B. So B was the example from the one before where it asked what's the field at that point that's inside a conductor. And inside a conductor is special because inside a conducting surface, the electric field is always 0. Okay, so let's look at why. So if I take, here's a conducting sphere, right? If I take a positive charge and I bring it close, let's think about what's going to happen to this conducting sphere, right? It's got mobile charges on the outside. So this positive charge is going to create a field that looks kind of like this, right? It's got field lines going out radially everywhere, but right, we're only concerned with these that are going towards this conducting sphere. Okay, and this doesn't have to be a sphere. It could be anything. It could be a rod or whatever, right? I'm just using a sphere because it's easy to draw. So what's going to happen inside of this conducting shell or object, right, because of this external field? Well, there's mobile charges, right? So if this is the positive charge, I'm going to get some negative charge that gets pulled to this side, right? Because it's attracted, it's moving opposite that electric field. And I'm going to end up with some positive charge on this side, right? Because as it pulls electrons towards this side, I'm left with positive over here. It's kind of like when you did charging by induction, right? If you bring something close, it pulls and it creates like this temporary dipole, right? So now I have this dipole over here, and what this leads to is that all of this charge, all of the excess charge is located on the surface, right? You can see from this, the furthest it can get to this positive charge is the edge of this surface, right? So all of this charge, excess charge I should say, exists on the outer surface. Okay, so we can get some other important things out of this and get to why it's 0. So if I take this and I draw a Gaussian surface inside, right? So I'm just going to draw a Gaussian surface right here, okay? If I go apply Gauss's law to this, I know that the electric flux is equal to the enclosed charge divided by the permittivity of free space. But I've already said that the excess charge sits on the outside of the conductor, right? So if all the excess charge is out there, that means that the enclosed charge is 0. And if the enclosed charge is 0, that also means that the flux is 0, right? So in this Gaussian surface on the inside, there can be no electric flux, which means if flux is electric field, where is it? Flux is electric field times area. If there's no flux, there's no electric field, right? Because the area is still a number. So from this, I can say that the electric field is equal to 0 inside a conductor. Okay, this only works for conductors. It's not like sometimes you'll deal with like a spherical charge distribution, right? If it's an insulator or if it's just a distribution of charge, this doesn't count. This is only for conductors. So this is the idea of a Faraday cage. Faraday cage is basically something metal that you can put something in and it keeps out external electric fields. Because if you apply an external field like this inside, if you look at what's happening, right, there's this separation of charge, and see how this field line right here, there's going to set up another field this way, right, between this charge separation, right, and there's going to be one right here, and there's going to be one right here, and those three are going to kind of cancel out what's happening. And so you could do this for every field line you could draw going through this shape. This internal field is going to cancel out that external field, right? Because these charges are going to come to equilibrium, and when it does that, the total electric field is 0. This works for any shape, right? I could do a box and apply an external field like this, right? So if I do it like this, my negative charges are going to come here, my positive charges are going to come here, and then there's going to set up this little internal electric field where this part and this part are going to cancel so that everywhere inside the electric field is 0. And so this also leads to another thing, right, that says the electric field is always perpendicular to the surface of a conductor. Okay, so let's think about what would happen if we had an electric field that wasn't perpendicular, right? So I'm going to draw a little thing here, right? So let's say we had an electric field that looked like this on that surface. Well, it's going to kind of be like this. It's going to pull charges one way or the other, and it's going to set up some field so that eventually there's going to be a separation of charge, and there'll be an electric field that'll end up being perpendicular. So no matter what, like it'll do, if there's an electric field like this, it's going to pull charges, right? And you're going to get a separation, and it's going to create a field that cancels out. So that field is going to go away. And the only thing you're going to be left with is any field lines that are perpendicular, right? Field lines that are perpendicular, that's the only way you can not have charges be mobile on the surface of that, right? Because if I have a field that points like this, that's going to cause charge to want to flow this way, which is basically a current. And that current's going to move charge until it eventually comes to equilibrium. The only way that it's not going to flow is these perpendicular field lines like this. So that's why the electric field always has to be perpendicular to the surface of a conductor. Okay, so I hope you got out of that the idea of symmetry and how to use like two of the basic shapes for Gauss's law, planar symmetry for like flat sheets, and for infinite sheets, right? You use a cylinder, and you can use planar symmetry, and then solving for spheres with spherical symmetry. And then using spherical symmetry as an example, it doesn't have to be a sphere, but we can see that net charge always resides on the surface of a conductor, right? Because that's the place that it can get the furthest away without actually escaping the surface. And then the electric field has to be 0 inside, because if I draw a Gaussian surface inside, all the charges on the outside, no electric field. And then the electric field always has to be perpendicular to that surface, because if it wasn't perpendicular, you'd have a movement of charge and then it would set up a canceling field. And eventually, no matter what, it's going to end up coming back to equilibrium where you have all those field lines pointing perpendicular.